Okay, hello everyone. Welcome to our fifth gathering, seminar, whatever we want to call it. Just a reminder again that these meetings will be recorded. This time we're going to go over the requirements for the next couple of weeks, which are actually nothing terribly formal. We should now be working on our projects, trying to get our prototypes up and running. That's possible, or at least doing some simulations, etc., and preparing the final report. Has everyone received answers to the question? If you haven't, please resend so it pops back up to the top of our list. Good evening, Hannah. I think we've got through everyone. If we haven't, as I said, send us an email to remind us. Okay, market research and costing plans have been marked by Savash. He's been through the whole lot. Hopefully you've all received your feedback. Generally, they were really, really well done. Very pleased with the level of content in both the market research costing plans and the videos. It's been quite impressive. Okay, so all the videos have now been marked completed. Feedback has been returned. Hopefully, again, you've seen all that. If you haven't received any feedback or you've got queries on it, don't hesitate to send an email to the IoT Capstone email address and we'll sort out whatever's needed. As I said, there's not any real content to the course for the next couple of weeks because we want to leave you free to work on those prototypes and get your reports ready. But that means we've got a little bit more time to spend if you do email us with any issues. And as the course is approaching its finalisation, I've set up a Facebook group so that we can keep in touch if you so desire. And if you've got questions, you can probably pop things on there too and see if we can get some of the instructors to answer you on any queries. So feel free to visit, like the page if you want to get updates, and we'll try and stay in touch after this is all over. Okay, so what are we going to run through tonight? Again, just a bit of a chat before we look for questions from you on your own projects. But at this point, we would hopefully have some idea of what we're going to try and build. We'll have some general layouts. We'll be testing out sensors, testing it out, etc. And that's great for the first stage of building prototypes. Once we've done our, and I'll use the term again, the Savash sticky tape prototype, we generally want to look at getting it to a stage which is closer to production. And we do this by, my watch is going off. We do this by starting to tidy things up and designing for that production run. And we'll go through a few of the tools we need to be able to do that. There's several aspects we look at. There's software development tools. We'll wonder why we don't use the Arduino IDE or similar sorts of programs. We should all be reasonably familiar with the Arduino or similar environments for development, and they serve a purpose, but they're not always the best option for software development. Once we've done the prototype, we know in general the concept is going to be working. We'll want to modify the hardware. Now, there's lots of reasons we want to modify the hardware, and we usually have different hardware for production. If we look at the standard sort of off-the-shelf boards, which are, as we've always said, great for prototyping, they get things up and running really quickly. You know the development board you're working on more than likely works correctly, so there's not a design flaw in it which is actually stopping you moving forward. But you do get to the point where you want to start to look at producing your own, particularly if you've got reasonably large numbers of items that are going to be producing. Reasons for doing this are, as I said, multiple. First one is to reduce the physical size of the device. Most of these development boards, as you probably noticed, have got lots of ports on them. They've got connectors so that you can get your digital I/O out to the sensors or whatever peripherals you're running. They have features on them, hardware features on them, which you don't actually use in your production. And all of these add to, first of all, the cost. So the cost of the board is higher. They take up valuable real estate, so the board is bigger. And because they're components running on the board that you're not using, they will still draw power. So if you're developing a battery-powered device, having all those extra components on that you're not using will shorten the battery life, and that is a critically important thing. So designing away from the wire prototype is important, and I'll show you some examples and the reason we do that in a sec. So once we've got our PCB, we've got to put it in something. We can't send out a printed circuit board all on its own. It needs to be inside a box. And there's, again, a number of options. And these options depend on a variety of factors. Probably the first to think of is where it's going to be used. Does it have to be weatherproof? Is it going to be something that could be damaged easily? Does it need to be physically secure? Is it going to be seen and touched by the users? So if it's seen and touched by the users, you've got to make it look nice and feel nice. And there's a range of ways we can produce these as well. Of course, the number we're producing is also a critical factor in what type of housing we would pick. So we'll have a look at that. So looking first at the Arduino type IDEs for our software development. These are great little programs because they're simple, they've got lots of built-in libraries, very quick to change anything on it, just a quick recompile, dump it down to your board and off you go. And you can also change the hardware very easily. So if you're going from Arduino Uno over to Arduino Nano, for example, you can use this, it'll recompile for that particular platform. You can download the software and generally it should run. However, to do that, things have to be designed in a very, very general manner. And as soon as you start designing for cross-platform or generalization, you start to lose efficiencies. And the Arduino IDE and the libraries it uses are incredibly inefficient, which means that the process has to be more powerful to perform the task that would otherwise be necessary. And it comes back again. If it's more powerful, we're going to use more energy, more power, and that will reduce battery life. Having a inefficient software library is also a drain on the power. So it has to run more. It'll require more memory. So again, that will cost you more. And it can actually have some what we term features, other people call bugs, in the system that you can't actually fix because it's somebody else's library. So you do have the flexibility, but you also lose some of the efficiencies and also some of the reliability. Another big advantage with it is things like Arduino IDE, they're open source and you don't have to pay license fees. In some of these development environments for commercial production, you do actually have to pay a license fee for every item you sell with software that's compiled on that platform. So they're the reasons not to use the Arduino IDE for the production level. Okay, so if you're not going to use the Arduino IDE, what do we use? Well, here we've got a little example. I'll let Sebash talk a little about this in a sec because it's one of his favorites. This is Code Composer Studio. It's designed specifically for the Texas Instruments platforms. This one's the MSP430, a mixed signal processor, and it is a fully featured development environment. What makes it different from the very simple Arduino IDE, it's nice, small, simple, easy to use, is it is not nice, small, easy to use at all. It's actually very, very complex, but it allows you to get into the hardware levels. So here we've got our C code in this case, and because it's designed specifically for a platform, so it is designed to only work with this MSP430 chipset, the code that it uses is optimized for that particular platform. Other things it can do, which is not terribly easy in the Arduino IDE, is you can include assembly language. Now, if you're not familiar with assembly language, you're a very lucky person, but assembly language is about as close as you get to talking in the real computer language. Each of these mnemonics, like this DC octal, relates to, in this case, would be a memory address. So it would be a number. If we're doing, and I'm not quite sure, do you know what that one does? Probably not. There's so many of them.
I think
people can't remember it.
It's probably a setup for one of the ADC
registers.
Yeah, probably.
Yeah, here it is. Set DCO to 1 megahertz.
Yeah.
This is the instruction in ones and zeros that would set our DCO, I would expect that's the clock oscillator, to run at 1 megahertz. So we can set the speed the CPU runs at through software. Because it's in assembly language and that is then turned directly into machine, it's incredibly efficient. So you can control all the registers, you can options, you can put it into sleep mode, all kinds of wonderful hardware tricks to make your code more efficient and to save power. The package in itself, and this is where things get really difficult, includes the ability to work with the hardware layout itself. So to be able to use a package like Code Composer Studio efficiently or with competence, you generally need to be a fully fledged computer engineer. You need to understand the hardware layout. You need to understand exactly what these 16-bit Sigma Delta do, how to work your interrupts through the pull-up and pull-down resistors. So it is a engineering task really to understand how to use this. It's also very good for large projects. It has a full for including files. It's fully capable of debugging code. So it has the debugger system in it, and you can step through code and watch individual bits. Savash, would you like to add something to this?
Yes, of course. So, speaking of interrupts, one of the common things we do with small microcontrollers and having a bunch of sensors is we usually have to have some sort of loop waiting for an event to be triggered from the sensor, say the change in a temperature, a change in a pressure, and when those changes come in, we'll respond to them, say by just turning off, like a very simple example, turning on a warning light. Now, with these sort of situations, if you're constantly just looking for the events to happen, you're wasting CPU cycles, you're wasting power. So the common practice is we use low power mode. So we turn off some of the peripherals in our microcontroller, we wait for one of those events to happen, and that event is going to cause an interrupt. That interrupt is going to stop our program, wake the CPU up, handle that, and go back. Now, these sort of IDs become useful because with interrupt, this is such a low-level interaction with your hardware, with your memory. When you want to stop the flow of your program so it loads other stuff in, you definitely need to have low-level control, and that's why you would need something like IA or Code Composer here. And one more thing I would like to add is you can write a C code like this directly in Arduino's IDE, but the problem with that is even though you can write that code and compile it, you won't be able to look inside the different registers. You wouldn't be able to debug it that well rather than just getting an error. But here you can actually see every individual line, step through the code line by line, and that it gives you those sort of capabilities.
Yeah, so writing code that is as bug-free as possible is absolutely critical in most embedded systems because they're installed once and they're never, or very rarely, updated. Hannes, would you like to make a comment on writing large code or large systems and the different approach you have to writing that as far as efficiency versus readability, maintainability?
There's a whole course of study really. That's what software engineering is all about. It's absolutely critical that when you write your code, it's done in such a way that it is really easy to understand, because it's, first of all, that makes it easier for you to spot bugs and avoid having them in production. But also means when you go and put the next one out, you can update your code. But that said, if you're working at a hardware level where code absolutely has to be efficient, then that's a trade-off. Most of software design and most things in life are trade-off, and that basically trying to make code very efficient rather than make it readable is a known trade-off. Another trade-off you'll be looking at is time versus space. If you have more resources, such as memory, you might be able to make things run faster, but if you have less resources, say battery power, whatever, you might just be able to slow things down and help there a bit. Is that more or less what you're talking about, Ian?
Yeah, it is. And this is where we have a fundamental difference between computing as a discipline and computer engineering as a discipline. We tend to, on the computer engineering side, look more at than maintainability and readability, even though it's still important. Whereas computing doesn't look so much at the efficiency, but is very much focused on the reliability, maintainability, and readability of code. And having a full package like this allows you to reach the reach an optimal stage of that sort of compromise. The other downside to this is cost. Arduino IDE is basically it's free, it's open source. Something like Code Composer Studio in a commercial environment is very, very, very expensive. I believe the license is somewhere around the 10,000 Australian dollar mark per seat. So not a cheap thing to have, but they do have limited versions, limited code size at a much lower or free price. One that we didn't mention tonight is IAR. I'm not sure if it's worth covering, but it's another option in the full IDEs that are available in embedded systems. You can talk about that a bit later, Savash, if we get a chance. Okay, so that's the software side, what sort of tools we would use to develop our software. The language is the same for the assembly, which is dependent on the platform. So if you can program correctly in a particular language, most of these compilers will and IDEs will work for you. So we get to one of my favourite bits, the Savash sticky tape prototype, which he's not actually responsible for this one, but I like stirring him up because he made a few the same. And this is a similar sort of thing to what Savash has been working on. It's an inertial measurement unit for measuring the movement of children with cerebral palsy. And as we can see here, it's a whole bunch of off-the-shelf boards. We've got a radio transmitter sitting here, a 2402 from memory. Here is our inertial measurement unit. Sitting underneath it is a pretty standard Arduino board and battery underneath that. Then we have our Vera board soldered on connectors, the wire hanging around, and this is held together with some double-sided tape. Now, the thing about it is it actually works really, really well. However, it's not overly reliable because wires break, parts move. It can't really stand being knocked about a great deal, which is not good when you're using this. And if you were doing it as a production, then it wouldn't be very nice if somebody actually opened up and saw this basically a mess sitting inside something they paid good money for. It also limits us in the size of the case we can have, and these cases were actually quite big. And one of the reasons that Savash is working on reducing the size by producing PCB is to get them small enough so they will fit on a child's hand. And that's why we want to take them over to something like these. These are ones we've built ourselves for different purposes. This is a text-to-speech engine, text and pronounces it either in Farsi, English, German, Spanish, and a couple of other languages. And we developed this ourselves because the board's text-to-speech engines at the time were really expensive. The board itself, we had manufactured in China, and they did the populating of the board as well. So they put the components on as well. It became, or it was, in fact, very, very cheap. I think these were about $25 each to produce when we produced a couple of hundred of them. And that was much cheaper than we could have made it, and much cheaper than using individual components and putting them together. Additionally, we got rid of all of the extra connectors. We could reduce the physical size quite dramatically, and we made it to fit the box that we're going to use. This is the same sort of thing. It's a ultrasonic guide for people with vision impairment, and it's just been reduced to a minimal size board on a device that sends out an ultrasound signal and vibrates when vibrates at the ratio of the distance, so it vibrates faster as you get closer to obstructions. Both of these boards were manufactured in China at very, very low cost, as I said. But the problem is that often the, I don't know, I keep saying the Chinese, but the developing country market where these things are made at a very low cost tend to be lacking a little in quality control. When we received these boards, yes, they were really, really cheap, but around 25% of them didn't actually work. So we had to either try and repair them or we threw them out, which is a waste of resources. But it was still cheaper than getting them produced locally. Another thing that they did is we specified that this was to be a half height for the clock, and they put in a full size crystal, which meant it didn't actually fit in the box. So we had to go along and pull off all of these crystals and throw them away and put new ones on. And that again was just because they didn't follow our specifications. So again, you've got to be very careful in the manufacture. You've got to weigh up the quality control against the cost, and make your decision based on that. If I was doing a very sensitive product, something that, say, for the health industry, I would not produce them outside of my personal control. So medical equipment I would get made locally so that I could supervise the production, do proper testing, etc., before it actually went out in products. So obvious question is, how do we go from this little device, this massive wires and sticky tape, over to something which is very artistic, beautifully laid out, and very pretty, and I've got one hanging on my wall. How do we get to that stage? Well, we use another application along the lines of this one. And again, the same as in the software, there are different tools for purposes. Fritzing is a really good one. It looks very, very similar to what we've used in Tinkercad, but it is not a simulator. It doesn't actually have that functionality. What you can do with it is lay things out as you would with Tinkercad, and at this point, I'm going to bring my fritzing. Are you fritzing? There you are. All right, can you see fritzing there? So Ash, is it on the screen? You're quiet, you're muted.
Yes, sorry, yes, it is.
Great. So here we have our normal setup that we've seen with things like Tinkercad. We put an Arduino board in, we've wired up some LEDs and a temperature sensor. Same sort of thing. As I said, it won't simulate. However, what it also does for us is it produces a schematic. A schematic is what the engineers use to lay the circuits out. Very, very important. This doesn't show us the details of what we're connecting to. It doesn't show how the wiring is done. And for testing and maintenance perspectives, it's not a good way to show a circuit. Schematic is crystal clear, makes perfect sense to the engineer. We can see that there's 220 ohm resistors here. We've got a red 633 nanometer LED here, a yellow one at 595 nanometers. We can see which pins they're connected to, and we can lay out the other devices, the temperature sensor in this case. So it's critically important that you show the schematic, because this is how we will talk to the engineers. Now, the fun bit of this is we can go straight and it will produce the printed circuit board for us. And this is how we're going to lay out our printed circuit board. We can move things around if we like. Yep. So hang on, I've clicked the wrong thing there. Bring it back over. Right, and you can see we're crossing wires over here, which is not a good thing to be doing. It allows us also to route the pin connection. So these are the wires that would be connecting that pin of the temperature sensor to ground. The middle one goes off to this. Sorry, this is where it gets a bit difficult to follow. There we go. Goes off to the A to D converter, and then we have a 5-volt supply running here. We click the auto route, it'll reroute things to suit where we've positioned them. So if we move it over there, auto route, it's worked it out. It's made a little change up there. The problem with the auto route in these free programs, such as Fritzing, is that they don't necessarily do a particularly good job. As we can see, this track is too close to this pin. When we try to solder it, it would actually join up. What it is very nice for is we can go and fabricate it. We click on that and it takes us off to the supplier, their preferred supplier, which is Aislia. We upload the project and it tells us here is the board it will produce, how much it will cost. In this case, it's €8 each, and we're getting 3 of them. We change that. Right, and you notice it's changing it by these multiples. That is because it works out how many it can fit on a raw piece of printed circuit board material. And in this case, it can fit 3, so every time we increase it by 3 because it's just as easy to produce 3 as it is to produce 1 because of that size of the board. As we can see, this is not terribly cheap. It's 26 euros for 3 boards. So, yeah, it's a tad expensive, but it is very easy. Go back to our... there's a lot of limitations in fritzing as well. It's limited to 2-layer boards only and a certain physical size. Okay, so fritzing's a really good one for hobbyists. Nice and easy to use, very quick. You get the boards made quickly and easily, but they're a little bit expensive. Moving to middle layer product, there is Eagle, which is produced by Autodesk, the same people who do Tinkercad. And they have a free version available, which allows you to have 2 signal layers and an 80 square centimetre board area. It has the advantage that it's more complete. You can do more in the placement, looking at the various features you've got. It's got a better library of components, which is important because you need the library of components to pick what sort of shape the device is going to take up, where the pins are on that particular device, etc. It's also cross-platform. So you can see here we're running it on Linux. We can also get a Windows version. I don't believe there's a Mac version, but I'm not certain on that. But it is cross-platform. So that's a nice middle-of-the-road one for PCBs. If you really want to go the whole hog, there are products like this. There's quite a few of them around. There's OrCAD. This is Altium Designer. Altium Designer is a full-blown design package. It will allow you to look at hotspots on the board. So if you've got an area that's consuming a lot of power and becoming quite warm, you can map where that is and look to where you have to pipe your cooling and adjust the fan, etc. It produces a full material, so you know what your component costs are, what the components are, where they go, etc. And it does mechanical designs for you. And this is really important when you're designing the case. So you lay out your PCB and you will be able to see what it looks like from a technical drawing perspective, but you can also render a 3D model of it as well and get a very good idea of what the end product will look like so that you can design your case to suit properly. However, has a couple of minor issues. It's extremely complex to use. We used to run courses in this particular package for experienced draftsmen and PCB designers, and the course was 7 days full time just to learn how to use this particular package. I've already experienced in PCB design, but just to use the package was a fairly intensive course. The other issue is it costs $25,000 per copy. So it's not something you would do or look at as a hobbyist. So very good, wonderful program to use if you can spend the time to learn it, but very expensive and very complex. If you were going to use something like this for a very large production run, and you would probably hire someone skilled in it to actually do the design for you. Okay, so we've done the PCB, we've got our software all working. We think we're finished, but we're not, because what we need... I didn't do that bit. And I've covered most of that, so I'll skip over anyway. I'll just mention this one. The fritzing was a little bit expensive. Some of the online stores, again, be aware of the quality control, but it can become very cheap. And this is one we've used a few times. What was the other one we used today? PCB Anytime?
I think so, yeah. And also PCB GoGo. I've posted the links for them.
PCB GoGo.
Yeah.
And we have...
So all PCB then. That's the other one.
We've used this lot, and they produced a set of 9 boards. They were about 3 inches long by half an inch wide, 75 by 12 or 13 millimeters. They could fit 9 of them on the sheet, so that's how many we ordered. And they cost us an entire whopping 99 cents. And that's not 99 cents each, that was 99 cents for all of them. So very, very cheap. The freight was, I'll say, $21. I think it was actually $25 to get them delivered. But the quality was okay. They were, as I said, incredibly cheap. And the delivery was just a bit expensive compared to the boards. If you look at this one, it's if we want it within 5 to 6 days is $185, but that means it's got 3 circuits on each side. So that is a complicated board to manufacture. And even at that, I'm not sure how many they're producing, how many we're producing. Even then, it's still only $200. So again, it's very, very cheap. But beware of that problem of quality control. Okay, so we've done our PCB, and now we need to do something that is every bit as important. We need to create something to hold the PCB itself. This is something the customer is going to see. So you need to make sure that it is of a quality and an appearance and durability that is suitable for the application. At the bottom, if we've got something that's going to sit outdoors, it's an agricultural product, for example, people aren't going to look at it very often. It's not a huge run of devices that you're going to produce. Something like the Jiffy box, which is these little black boxes over here. I hope you can see my mouse. Number one, they're very cheap. You can get them in weatherproof fusions. They come in a huge variety of sizes and shapes. And you design your PCB to fit inside them, and you've got this ugly little box which you can hide in a corner where nobody's going to see it. But it is cheap, it is quick, and they're readily available from multiple manufacturers. So Jiffy boxes are great for either small run or runs where the device itself is not going to be in a common sight. Not much more to say on those. They're usually only a couple of dollars each, so they're very cheap, and you don't have to tool up for them. The next option is 3D printing, and this is becoming more and more popular. I chose this particular image because it shows the main disadvantages of 3D printing. We can see the quality isn't that great. We've got all of the lines where each individual layer of material has been layered down to produce the device. We've got a pattern on the which is not intentional. That's the pattern that's come from the bed it was printed on. So you've got this textured finish, which is not very pretty, and it's terribly uneven normally. But more importantly, it's printed, and we see as we look along here, all the way down is not the same. It's not just the photo. We've had some warping in the printing of this device, or this package, which is very, very common in 3D printing. So here we've got a disadvantage. If you're doing 3D printing and you're trying to maximize throughput, produce the case very quickly, quality can suffer. The plus side of this is it's very quick to make changes. So you print one, didn't quite work, so you modify it and you print another one. And you can try everything out for, as I said, the design prototype or manufacturing prototype. If you've got very small runs, it's a good way to go. You can improve this print quality by using a better printer or slowing down the print rate. There are ways to improve the as well. We'll go into that. But it does make for a very good prototype, and as I said, very, very cheap material-wise. The material on 3D printers, the filament type, generally between $20 and $40 a kilo, and you can make an awful lot of housings with a kilo of plastic. However, they are very time-consuming. Something like that box sitting there would probably take somewhere around the 4 to 6 hours to print, depending on the quality you're printing at, and you'd only be producing one at a time. For the initial prototypes or modelling device housings, but not the best way to do for production runs. One of the mid-range steps is where you get devices or housings like this. This is a vacuum casting housing. It's produced by heating plastic until it becomes plastic, which is a term for being pliable. You pull it down over a mold and you use a vacuum to pull it into shape. These are reasonably rugged. The quality is, again, mid-range. The cost is reasonably low, but you've got to pay for the cost of the made up, and are quite often used in fairly low-run, as in the hundreds, low-run productions. If you're getting to the point where you're in producing very, very large numbers, the most accepted way of producing the casings, and it's not a casing, it's a chess piece, merely machine out 2 matching pieces of steel, and I used to have a company that made these, so I know how they're made. They're put together and you inject it with a liquid form of the material that you want to produce the housing in. This makes them very, very cheap. The material cost is relatively low. Again, it's cheaper than the filament plastic because you're buying it in bulk. It can be used very quickly. It can produce things very, very rapidly. The problem is that the machines are also large and expensive to injection molding, which means most of the manufacturers or the people who you would get to do the injection molding for you wouldn't even look at turning the machine on unless you were producing 10,000 of a particular item. It's just not worth their time with the wastage and the setup. So you need very large production runs for that. The other factor is this little thing, and that's what I used to, well, I didn't personally, but my people used to make, and they are the dies for producing the injection molded piece. These are very, very high tolerance, intricate pieces of equipment. Something like this, which would only be, probably looking at the thickness of these, probably only 4 inches by 6 inches in size. Something like that I would cost around about the $40,000 mark. So just to start, you've got a $40,000 investment, and then you need to produce at least 10,000 of the item to get someone to actually fire up their machine for you. So you're looking at very, very high cost initially. However, producing the item like this is actually your smallest cost. It's almost a zero cost when compared to the setup costs. So if you've got large runs requiring very high quality output, because you can get very high quality out of injection molding, this is the way to go. But as I said, you do need very, very large runs. Okay, I'll come back to that. I just wanted to show one little thing showing how we can use 3D printing. If I can find it, it's here somewhere. There it is. Getting your prototype to a manufacturing prototype or design prototype position. Here we've got a very pretty motorcycle. Looks good. It doesn't work. It is not a real motorbike. That motorbike is a full-size 3D printed production prototype. And what they've done there is they've actually 3D printed most of the parts. You can see some of the engine parts here. The wheels been printed there, and then fitted it all together to make sure everything actually fits. Worked out how they can manufacture this motorbike, given the particular parts, get their manufacturing processing done, and show what the bike will look like in the final production run without actually having to produce a real working motorbike. And we do the same thing with our electronics. We go through our sticky tape prototype, we move to a design prototype or manufacturing prototype like this motorbike is here. And then once we've got all of the fit, the mechanical and the artistic, if you like, attributes sorted out, we would move to our actual production. So coming back to this, we'll just one other little thing to do. Okay, so that's what we wanted to just talk about a bit tonight. A little reminder, we finish up the this MOOC in a couple of weeks, I think actually 3 weeks, 2-3 weeks. But we won't be closing it off for another 2 weeks after that. This is to allow us time to get the marking done, get your marks in, give you feedback, make sure everything is nicely finalised, everyone's happy, before the course gets archived and moved off. During that time, we're going to keep our chats running along. Next fortnight, we will have David McMeekin joining us. Is he here tonight? I thought I heard him.
Yes, I think he's still here.
Okay. David, would you like to just give a brief rundown of what you'll be talking about next fortnight? You'll be better at it than me. You might have wandered off.
No. Sorry, I just couldn't find the unmute button. So
I'm sure it actually woke you up.
Yeah, okay. Yeah, I was off doing other thing. No, I just was. Yeah. So the next couple of weeks, we'll just take a look at some basics in some location data and processing location data, and some of the ways the simple storage techniques or file structures that we can store location data in, and some of the particularly the Python libraries that we will use or can use to process data, sort of GPS data or anything location based, so that we can then look at visualizing it onto a web map or something along those lines. So that's, I think, what we'll be looking at in the coming couple of weeks.
Okay, great. And the thing is that, using GPS with your IoT device, that sort of stuff, that's really going to be quite interesting. The following 2 weeks, when we're actually complete through some big data and data analytics stuff to begin with, and we'll have our chat afterwards. So that's all we wanted to actually talk to you about, and now we'd like to know if you have any questions.
So feel free to use the raise hand option next to your names, and I'll unmute you so you can ask your question, or you can type it in the chat. So Anton has a question. Go ahead, please. Yes.
Excellent. My question is around, so far we saw PCB, how to create stuff like this. But question is around PCB assembly. Like my question is, maybe you can share 1, 2, 3 services which able to deliver the PCBs.
So out of the ones I posted, I know PCB GoGo and all PCBA, they both offer assembly as well, and they usually tend to be not that cheap depending on how many layers you end up having for your PCBs. I know Ian has recently ordered some. You mentioned something this morning about the assembled ones. You've done, I think you're unmuted, Ian. Muted?
No. Okay, I'll just look for. Where's he gone? Ah, there we go. Okay, so when you're doing this, PCBs are hard to build nowadays, and I'll just go back to this briefly to show you why. There we go. These are not high density boards, so these ones don't have a massive number of components on it, but that's a 5mm push button, so that's not that big, and it's not that far off actual size on the screen here. Trying to get a soldering iron in to actually solder on these surface mount components is nigh on impossible nowadays. And particularly when you start to get things like the IMU chips, which are only 1.5mm by 1.5mm, and have 16 odd pins, I think, don't they? Something like that anyway. And it's not humanly possible to do these things manually anymore. So we would tend to go and do the PCB assembly bit on these sort of sites. It doesn't turn out too bad usually, particularly because they get much better buying prices on the components. So when you send your PCB up to them, you send them the Gerber file, which is a particular, I should mention, a particular type of format that's used to describe how printed circuit boards are laid out, named after one of the early machines that used to do it. But then you also need to send them, go back to our fritzing, you also need to send them this along with the bill of materials so that they can see that you're using an Rev 3 LM35 temperature sensor. And the bill of materials will also include what package each of those devices is coming in. And this is where things like fritzing aren't great because they won't do that population. But if we have a look at the picture, but in here we've got all of the physical dimensions and the footprint, as it's termed, of every single component that's used. So if they're going to do the manufacture for it, you need to be able to produce this bill of materials. You need to be able to produce the schematic diagram as well, and you supply that to, and they will then lay the pieces of the PCB and supply you a printed circuit board exactly like that one. Well, laid out like that one, because this one was actually manufactured in China with the PCB manufacturer. We had Serge do this one by hand, and he said he'd never do it again. So that answers your question. If you're going to do something that has very high density components on it that are surface mount with very fine pin pitch, then you need to or should really get one of the PCB manufacturers to do the board population for you. And as I said, they buy the components in huge numbers and they'll get them at a much better price than you can. Just again, be aware of the quality control issues that can happen. Make sure that they do proper testing. If we go and have a look at this, see that they should have some there. Assembly.
Yeah, so some of them, I know all PCB
testing and
they do offer some sort of testing. Not all of them do. Some of them just you give them the file and just
look like this lot does. But the testing can be very expensive as well. There we go. Testing procedure, X-ray, in-circuit testing. Yeah, so they do.
Yeah.
Is that the kind of thing you're after?
Yes, it says thanks in the chat. So if you don't mind, Antoine, turning off that raise hand so anyone else wants to ask any questions. And while Ian was going through the slides, I did post a bunch of links to the chat to Freezing IAR Code Composer if anyone were interested in any of them. And I just checked, there seems that there is a Mac version of Eagle.
Oh, there is? Okay.
Yeah, Mac and a Linux version. And with IAR, they offer a 8 kilobyte limit size version of IAR, which should be fine for prototyping, and it's unlimited. You just have to register for it. They offer a 30-day trial one and a size, and then there's the second option is a size limited one. But that's not too bad.
Yeah, this doesn't really show, but
I'll post the link.
Screenshot. Yeah, there's free trials. Get it to try for a little while. But these are the sort of things that are really crucial. The fact that you've got a debug, you can trace signals on the boards itself, runtime, and you can do the secure programming as well. They're really critical things that are in these real packages rather than the hobbyist type packages. And it covers lots of different technologies. But again, it's a fairly complex system to use.
Any questions? Okay, we had something from Antoine. We got a sample of final project. Maybe you can share some comments. Oh yes, Ian, there was a sample of the final report. You went over it.
Yes, and it should be up on edX as soon as we've got some staff back. But I did put on the discussion board a link to my Google Drive so you can grab this beforehand. And here it is here. So we'll run through that. This is just a very quick sample that I did. Diagrams in it are not relevant. The references aren't relevant, but it's more just to give you a layout and a style. So what we're looking for is around 20 pages of text, not counting the table of contents, table of figures, and not counting references. So I've laid it out in a similar manner to what we would like, but you're not tied into doing this. Key things are to introduce the problem, make sure you explain that properly, and this should be taken pretty much from your Canvanizer template if you get up to date. So the Canvanizer should cover most of that, and that's what we cover in there. It's a bit on the writing style. You should write in third person past tense, which means you don't use the terms I, me, you, etc. And because you're reporting completed, it should be written in the past sense. That's just a little bit of practice for those who plan to complete the full master's degree at Curtin, you'd need to write a full thesis on your developments in your time doing that program, and it has fairly strict guidelines. With referencing, you can reference any style you're happy to use. I've used IEEE as an example. It's a really nice, straightforward, simple referencing style, and it's an example. I just threw some in around. There we go. There's some examples there. Where did I put one in text? I've got one here somewhere. There we go. So it's just a square bracket with the reference number in it. And if we go down, number 1 in our reference list, we see is T. Brown, an interview by founder. And it's just a fairly standard format like that. What else is important? Always label and reference your figures. So if it's not your work, you should have a reference for it. That way you're not claiming it as your own. Just random diagrams in to show the kind of format we would expect. As I said, it's mostly just to give you an idea. So it's a report about writing a report, except for one of the conclusions I threw in here, which was just one of our past students. Just the conclusion that he put in to give you an idea of what the conclusion section should be like. So I should actually share that link again. Bear with me a couple of seconds and I'll grab it. See if anyone else wants anything or if that's clear or not, and I'll...
Okay, so if anyone has any questions, please, again, feel
post it in.
I've got a question. Could I share that with our thesis students? Because they were looking for some samples. Or
not this one. I'll dig something else up for them. This is not as anywhere near as formal as our requirements for thesis.
Sure.
Yeah. What do I have? Let's go down here.
So Aditya asked, what's the criteria for completing a master's at Curtin?
Okay, it depends which masters you want to do, but if you want to do the engineering one, you need to have a bachelor's degree of some kind, preferably in, actually not prefer, you have to have, for electrical engineering, you'd have to have a bachelor's degree in engineering, obviously, computer science, mathematics, or physics. And if you're from a non-English speaking background, you have to meet the IELTS 6 levels. Apart from that, I think that's about it to do the Masters by coursework.
Yeah, I think that's pretty much it.
If you've got a 3-year degree or a science degree, the Masters itself is actually 3 years long. I know that sounds terribly long for a Masters, but it's engineering. But you would get credit for some of the units, and you get 25% or 100 credit points from the MicroMasters as well. 100 credit points, I should explain, that's 6 months. Yeah, I'm just trying to find where I've hidden that. Oh, of course. Right down the end. There we go. Share. Grab the link. All right. I'll have to stop sharing my screen and put the link in chat, so just bear with me again.
Okay. We have about 4 or 5 more minutes, everyone. Okay.
So if you just click on that, it'll take you to my Google Drive, and you can copy it down from there. But as I said, it should be up fairly shortly on edX. Okay, so hopefully everyone's making some progress. More than happy to chat to you further if you would like. send us an email with any questions, and we'll try and get back to you as soon as we can. But as I said, we've been very impressed with the quality of the submission so far. Good, interesting stuff going on. Okay, 5 minutes early.
Ian, I'm gonna set you as the host so we can do the stopping and the stuff. And I think we have Mazin here who wanted to have a one-on-one meeting with us right after this one, so he's gonna stick around in it.
So everyone's happy with how they're going? Any further info or something we can help with? Okay, well, thank you everyone. It's been good to see you all again. As I said, next week we will have a bit of a chat on location-based services, GPS, compliments of Dr. McMeekin. And the following meeting, we will have some interesting stuff on data science, data analytics, predictive analytics, and all kinds of buzzwords from Valerie. Valerie couldn't make it tonight. She's at a fancy dinner for the National IT Association. Okay. Have a chat to Mason, no?
See you later, guys. Have a good one.
You too.
See you.
Not all. Or good day, I guess, depending on where.
Good whatever.
Yeah.
Thanks a lot. Bye. Ciao.
If you want those links sent through, we can do that too for the PCB manufacturer. But you can search for anything. There's lots of them out there.
I was copying actually the links that was shared in chat, and my question was around maybe you used as well with C the Studio. Maybe you heard about they covered as well PCB manufacturing and assembling.
Yeah.
But I already got your answer that you use it all PCB service and works.
We also use a local company when we need the high quality stuff.
Huh.
I think the important thing is make sure that whichever one you choose, they do testing. All of them offer that testing service.
As I've used it for services, I don't know. They might tell that they provide the service.
They would say because it would because they would ask you to pay for it. Otherwise, so if they don't mention anything about testing, so that probably means that they don't offer it.
Okay, look, got my questions. Got my answer. Thanks a lot. I will probably send mails later.
Okay, no worries.
Great.
Thank you. Bye.
No worries. See you later.